At the far end of time, beyond stars, beyond galaxies, beyond everything we recognize, the universe is heading toward a silent conclusion. Not with an explosion, not with fire, not with darkness falling suddenly from the sky, but with something far more unsettling: total cosmic stillness. Physicists call it heat death, the moment when the universe runs out of usable energy, when temperature differences vanish, when motion fades, when no work can be done, when time itself loses meaning. In this future, stars no longer shine, black holes slowly evaporate, atoms drift apart, and even the memory of structure disappears. Everything that ever happened, every civilization, every planet, every galaxy, becomes mathematically irrelevant. Entropy wins. In today's documentary, we will travel billions and trillions of years into the future to understand what heat death really means, why physics predicts it, how close the universe already is to this fate, and what remains when the final light goes out. If you're fascinated by deep space, cosmic endings, and the ultimate fate of reality itself, make sure to subscribe now, because this journey goes further than any star, further than any black hole, and further than time itself. This is not science fiction. This is the final chapter of the universe, and it has already begun. The story of heat death does not begin in the distant future. It begins right now, in the quiet physics of everyday reality. Every second that passes, the universe is changing in one specific direction, not toward chaos, but toward balance, toward sameness, toward a state where all useful energy is spread so evenly that nothing meaningful can happen anymore. This direction is controlled by one of the most powerful laws in all of physics, the second law of thermodynamics. It states that entropy, a measure of disorder and energy dispersion, always increases in an isolated system, and the universe is the largest isolated system that exists. Entropy is often misunderstood as messiness, but in cosmic terms it means something more precise. It means energy moving from concentrated, useful forms into thin, unusable forms. Hot objects cool down, cold objects warm up. Energy spreads out, differences disappear. Life, stars, motion, and structure exist only because energy differences exist. Heat flows from hot stars into cold space. Chemical reactions occur because molecules are unbalanced. Gravity creates motion because matter is unevenly distributed. When those differences vanish, activity stops. The universe does not die in the dramatic way movies imagine. It slowly relaxes into equilibrium, a cosmic flat line. Right now, the universe is young enough to still be full of gradients. Stars burn hydrogen into helium, galaxies collide and rearrange matter. Black holes consume energy, radiation streams through space. All of this produces entropy. Every photon emitted by a star carries away organized energy and converts it into low-grade heat, dispersed across the cosmos. Every fusion reaction inside a star pushes the universe one step closer to thermal balance. This is not optional. It is built into the structure of reality itself. To understand why heat death is unavoidable, we must first understand how the universe uses energy. The early universe was incredibly hot, dense, and uniform, but tiny quantum fluctuations created slight differences in density. Gravity amplified those differences. Matter collapsed into stars and galaxies. This created structure, and structure allowed energy to do work. Stars formed, planets cooled, chemical complexity emerged. Life became possible. But structure is temporary. Stars do not create energy. They only convert stored nuclear energy into radiation. Once their fuel is exhausted, fusion stops. Low-mass stars will fade quietly. Massive stars explode. White dwarfs cool. Neutron stars lose heat. Even black holes, the most extreme energy traps in the universe, are not permanent. They slowly leak energy through Hawking radiation. Nothing escapes entropy. Over vast timescales, the universe transforms from an engine of change into a cold archive of dead matter and thin radiation. But heat death is not about cold alone. It is about energy availability. A system at maximum entropy may still contain energy, but none of it can be used to perform work. No engines can run. No stars can shine. No chemistry can occur. Everything is spread too evenly. Imagine a room where the temperature is perfectly uniform everywhere. You cannot extract energy from that room. There is no hot side and cold side, no flow, no movement. The universe is moving toward that same state, but on a cosmic scale. As expansion continues, galaxies drift farther apart. Gravity becomes weaker between distant structures. Matter thins out. Radiation stretches into longer wavelengths. Energy becomes colder and more diluted. The universe is not collapsing. It is expanding into stillness. This expansion plays a critical role in accelerating heat death. As space stretches, it carries energy with it. Photons lose energy through redshift. Their wavelengths grow longer, their temperatures drop. This means that even existing radiation becomes less useful over time. Energy is not destroyed, but it becomes less capable of creating structure. Dark energy makes this process even more severe. It accelerates cosmic expansion. It pulls galaxies apart faster than gravity can hold them together on large scales. Over trillions of years, galaxies outside local clusters disappear beyond the observable horizon. The universe becomes increasingly isolated. Each region becomes its own island of dying matter. Inside those islands, stars will eventually exhaust their fuel. After about 10 trillion years, normal star formation will largely end. Hydrogen becomes scarce, gas clouds thin out. The birth of new stars slows to a halt. What remains are stellar remnants, white dwarfs, neutron stars, black holes. These objects still contain energy, but they are slowly losing it. White dwarfs cool and fade into black dwarfs. Neutron stars lose heat and radiation. Black holes evaporate over unimaginable timescales. A stellar mass black hole may take 10 circumflex 67 years to disappear. Supermassive black holes may take 10 circumflex 100 years. But they do vanish. When the last black hole evaporates, something extraordinary happens. The universe enters the final phase of heat death. No stars, no massive objects, no energy gradients. Only thin particles and stretched radiation drifting through near-perfect darkness. Time itself becomes meaningless in practical terms. Nothing changes. Nothing evolves. Nothing reacts. The universe becomes a static, maximum entropy state. This is not emptiness. It is fullness without usefulness. Energy exists everywhere, but nowhere in a form that can create structure. From a physics perspective, this is the most stable configuration possible. The universe has settled into equilibrium. But from an existential perspective, it is the end of everything recognizable. No complexity, no chemistry, no life, no information processing, no memory. Everything that once happened becomes buried in entropy. Even the concept of future loses significance because nothing new can occur. This outcome is not based on speculation. It emerges directly from well-tested physical laws, thermodynamics, cosmic expansion, quantum radiation, gravity. Together they form a consistent picture of long-term cosmic evolution. Heat death is not dramatic. It is slow, relentless, unavoidable. It does not require disaster. It requires time. And time is the one resource the universe has in unlimited supply. What makes this scenario so unsettling is not just the end itself, but the realization that the universe is already moving in this direction. Every star burning today is contributing to that final equilibrium. Every galaxy collision increases entropy. Every photon escaping into space pushes the universe closer to uniformity. The heat death is not something that will suddenly happen. It is happening continuously. Right now, at this moment, on scales too slow for human perception, but inevitable. In the next part, we will go deeper into the timeline of this cosmic ending, from the final era of stars to the slow decay of matter itself, and the strange physics that may dominate the universe when everything familiar has vanished. Because heat death is not just the end of stars, it is the end of structure, the end of motion, and ultimately the end of time as we understand it. After the universe finishes burning through its bright, active era, a far quieter chapter begins. This is the long twilight of existence, a period so vast in duration that human history becomes insignificant by comparison. It is here that heat death becomes more than theory. It becomes the dominant direction of cosmic reality. The first major transition begins when star formation slows and finally stops. Stars exist because clouds of hydrogen collapse under gravity, but hydrogen is not infinite. Each generation of stars converts raw fuel into heavier elements. Over trillions of years, the supply of easily usable hydrogen becomes exhausted. Gas clouds grow thinner. Collisions become rarer. Gravity no longer has enough material to build new suns. By roughly 10 trillion years into the future, the universe enters what scientists call the degenerate era. This is the age of stellar remnants. The night sky no longer glows with new stars. Instead, it becomes dominated by the corpses of ancient suns. White dwarfs drift silently through space, the dense cores of former stars that once burned brightly. They no longer produce energy. They only slowly radiate away the heat stored in their compressed matter. Neutron stars remain as ultra-dense stellar skeletons. They are city-sized objects with masses greater than the Sun. Over time, they cool, their magnetic fields weaken, their radiation fades. Black holes dominate the mass of galaxies. They grow through mergers and consumption of nearby matter. In this distant era, supermassive black holes sit at the centers of dead galaxies like frozen engines that no longer power anything meaningful. Galaxies themselves change. Without new stars forming, galaxies grow dim. Spiral arms fade. Dust clouds disappear. The beautiful structures seen today slowly dissolve into collections of faint stellar remnants orbiting invisible gravitational centers. Cosmic expansion continues to stretch space. Galaxies outside local groups disappear beyond the observable horizon. Light from distant clusters becomes so redshifted that it fades into radio wavelengths longer than the size of the observable universe itself. Eventually, even the cosmic microwave background, the afterglow of the Big Bang, becomes undetectable. Its photons stretch into wavelengths larger than the universe's horizon. The universe loses its oldest visible memory. At this stage, the cosmos becomes dark in a way that is difficult to imagine. Not dramatic darkness, not sudden blackness, but a slow erasure of light. Every remaining source of radiation weakens. Every remaining heat source cools. Every process that once created motion slows down. Yet the universe is not completely static yet. Something remarkable still remains active. Black holes. For a long time, black holes were believed to be eternal, perfect traps, endpoints of matter and energy. But quantum physics revealed something unexpected. Black holes are not truly black. They emit radiation. This process, called Hawking radiation, occurs because of quantum fluctuations near the event horizon. Over incredibly long timescales, black holes lose mass. They shrink. They evaporate. This evaporation is unimaginably slow. A black hole with the mass of the Sun would take about 10 circumflex 67 years to disappear. A supermassive black hole may take up to 10 circumflex 100 years. To put that in perspective, the current age of the universe is about 10 circumflex 10 years. These timescales are so enormous that normal intuition completely fails. But given enough time, even black holes vanish, and when they do, they release their final energy in a faint burst of radiation. After the last black hole evaporates, the universe enters its most extreme phase of heat death. There are no stars, no galaxies in the traditional sense, No massive gravitational structures, only low-energy particles and stretched radiation drifting through expanding space. This era is sometimes called the dark era, but it is not dark in the sense of shadow. It is dark because nothing produces meaningful light anymore. Photons exist, but they are so low energy that they no longer interact in significant ways. Matter becomes rare. Protons and electrons may remain, but their interactions become extremely unlikely as space expands and particles drift farther apart. Collisions become so rare that chemical reactions effectively stop. No new atoms form, no molecules assemble, no structures emerge. Everything becomes isolated. Time continues mathematically, but physically it loses relevance. Without change, time has no observable meaning. Entropy has reached near maximum levels. The universe becomes a nearly perfect equilibrium system. At this point, the heat death is complete. Not as an event, but as a condition, a permanent state of cosmic stillness. But the story may not end there. Some theories suggest even matter itself may not be eternal. Protons, the building blocks of atomic nuclei, might decay. Proton decay has never been observed, but many grand unified theories predict it. If protons decay, then even the last atoms will eventually disintegrate into radiation and elementary particles. This process would take at least 10 circumflex 34 years, and possibly far longer, but if it occurs, it removes the final remnants of conventional matter from the universe. What remains is a thin soup of photons, neutrinos, and low-energy particles drifting endlessly through space. No structure, no complexity, no organization, only entropy. Even information becomes meaningless. Physical records require stable structures. Without atoms, without molecules, without energy gradients, nothing can store information. Every trace of the universe's past becomes physically inaccessible. The heat death is not destruction, it is forgetting. The universe does not explode. It does not collapse. It simply loses the ability to remember itself. From a thermodynamic perspective, this is the natural endpoint of any closed system. Energy spreads, differences vanish, order dissolves. The universe becomes maximally probable, the most statistically stable configuration possible. This is not failure, it is the logical conclusion of physical law. What makes this future so strange is that it is not violent, it is quiet, gentle, relentless. It is not marked by dramatic catastrophes, it is marked by patience, the patience of physics, the patience of entropy. Every second that passes brings the universe microscopically closer to this equilibrium. The stars we see today are temporary beacons in a very long cosmic night. Their light represents borrowed energy from a finite supply. Once that supply is gone, the universe does not replace it. There is no cosmic reset button, no natural mechanism to reverse entropy on a universal scale. The arrow of time points in one direction, forward, toward balance, toward uniformity, toward heat death. In the next part, we will explore the most unsettling implications of this scenario, what heat death means for information, memory, consciousness, and whether physics allows any escape from this ultimate fate. Because the true horror of heat death is not darkness, it is silence. The silence of a universe that has nothing left to say. As the universe drifts deeper into heat death, the most disturbing consequence is not the disappearance of stars or the fading of galaxies. It is the fate of information itself. Because at its core, the universe is not only a collection of particles and energy, it is a system that stores, transfers, and transforms information, and heat death threatens to erase that system entirely. Information exists wherever structure exists. A crystal lattice stores information in its atomic pattern. DNA stores information in molecular sequences. A star stores information in the arrangement of its plasma layers. A galaxy stores information in the orbits of billions of stars. Even memory, thought, and consciousness depend on physical information encoded in matter and energy. But information requires stability, It requires low entropy. It requires organized arrangements that resist randomization. As entropy increases, information becomes harder to preserve. Patterns dissolve, structures blur, distinctions fade. Heat death is the ultimate information eraser. When the universe reaches near-perfect thermal equilibrium, all physical systems become maximally randomized. Particles spread out, energy becomes uniformly distributed. There are no gradients, no contrasts, no organized arrangements that can store meaningful data. This does not mean that information is destroyed in the technical sense. According to quantum mechanics, information is conserved, but conservation does not mean accessibility. Information can exist in forms so scrambled, so dispersed, so entangled with random noise that it becomes practically unrecoverable. In heat death, information still exists mathematically, but it becomes physically unreachable. This distinction is critical. Imagine shredding every book ever written and scattering the paper fragments across the ocean. The information technically still exists, but reconstructing it becomes functionally impossible. The universe undergoes a similar process. The story of everything that ever happened becomes smeared across space-time. Not erased, but lost beyond recovery. This has profound implications for memory. Memory requires stable structures that persist over time. Neurons store memory through chemical and electrical configurations. Computers store memory through magnetic or electronic states. All of these rely on energy gradients and controlled environments. In a heat-dead universe, no such environments exist. There is no temperature difference, no power source, no physical medium capable of holding long-term structure. Memory becomes impossible, not forgotten by minds, but erased by physics. Even if a form of life somehow survived into the far future, it would be unable to store experiences. Without memory, identity collapses, consciousness becomes unsustainable. This leads to one of the darkest implications of heat death. It is not just the end of life, it is the end of meaning. Meaning depends on continuity, on cause and effect, on memory linking past to present. In a universe where nothing changes, meaning has no anchor, time becomes directionless. Without events, there is no narrative. Without contrast, there is no experience. This is why physicists sometimes describe heat death as the thermal equilibrium of nothing happening, but the consequences go even deeper. Heat death also challenges the concept of time itself. Time is not just a ticking clock. In physics, time is tied to change. Processes define the flow of time. Entropy defines the arrow of time. As entropy increases, time appears to move forward. In heat death, entropy reaches maximum. No further increase is possible. No macroscopic changes occur. From the perspective of physical processes, time effectively stops. Clocks cannot tick because ticking requires energy differences. Chemical reactions cannot proceed. Motion becomes statistically meaningless. The universe still exists mathematically in space-time, but physically it becomes frozen in an eternal present. This creates a strange paradox. Time continues in equations, but disappears in experience. A universe with no change is indistinguishable from a universe with no time. This leads to another unsettling idea. Heat death does not end the universe. It traps it. The universe does not vanish. It remains trapped in a static state with no internal evolution, existence without experience, presence without process, being without becoming. From a human perspective, this is more disturbing than destruction. Destruction implies transition. Heat death implies stagnation, an eternal plateau of nothingness. But could anything disrupt this fate? Physicists have explored possible escape routes, quantum fluctuations, vacuum decay, cosmic phase transitions, exotic physics beyond the standard model. Some theories suggest that even in maximum entropy, tiny quantum fluctuations could still occur. These fluctuations might create brief pockets of energy imbalance, but these would be extremely rare and isolated. They would not restore structure on cosmic scales. Others propose that the universe might undergo a vacuum transition, a shift to a lower energy state of space-time itself. If such a transition occurred, it could radically alter physical laws, it could destroy existing structure, or create a new form of universe. But there is no evidence that such a transition is imminent or even likely. And even if it occurred, it would not preserve the current universe. It would replace it. From the standpoint of continuity, heat death still represents the end of this universe's story. Another proposed escape involves cyclic cosmologies, universes that collapse and restart. But current observations show accelerating expansion, not contraction. The evidence strongly favours a future dominated by dark energy. Expansion will continue, not reverse. This makes heat death the most consistent long-term outcome based on known physics. Some theories speculate about Boltzmann brains, hypothetical self-aware fluctuations arising randomly in a heat-dead universe. In a universe with infinite time, random quantum fluctuations could theoretically assemble brief conscious systems. But these would be unstable, short-lived, and disconnected from reality. They would not rebuild civilization. They would not restore structure. They would be momentary sparks in an ocean of entropy. Even this strange idea emphasizes how empty the future becomes. When the most optimistic possibility is a random hallucination of consciousness, the depth of heat death becomes clear. Another unsettling implication concerns the fate of causality. Causality depends on sequences of events. Cause produces effect. Effect becomes cause. In heat death, this chain breaks. Without processes, there is no cause and effect. Events do not propagate. Interactions do not occur. Reality becomes static. This removes the fundamental engine of physics. No interactions. No reactions, no evolution. The universe becomes a solved equation with no variables left to change. And yet, heat death is not sudden, it is unimaginably slow. This slowness is what makes it both inevitable and invisible. Human lifetimes are too short to notice the drift toward equilibrium. Even civilizations lasting millions of years would barely perceive the change, but the direction is fixed. Entropy increases with absolute certainty. The arrow of time does not reverse. The universe cannot decide to stop obeying thermodynamics. This inevitability is what gives heat death its power. It is not a scenario dependent on chance. It is a consequence of the fundamental structure of physical law. Everything that exists today is borrowing order from the past. Eventually, that borrowed order runs out. What makes this particularly profound is that the universe began in an extremely low entropy state. The Big Bang was not maximum disorder. It was highly ordered. This initial condition made stars, galaxies, life, and complexity possible. Heat death is the return to equilibrium. The universe starts ordered, ends uniform, begins with structure, ends with sameness. This arc defines cosmic history. From differentiation to uniformity, from complexity to simplicity, from motion to stillness, from memory to forgetting. And yet, within this bleak future lies a strange beauty. The universe follows its laws perfectly. It evolves according to elegant mathematical principles. Heat death is not chaos. It is the most stable configuration possible. It is the universe completing its thermodynamic journey. This does not make it comforting, but it makes it consistent. In the next part, we will confront the deepest question heat death raises. If everything will eventually be forgotten, why does anything exist at all? And what does this ultimate ending mean for life, intelligence, and purpose in a universe that is slowly running out of time? Because when physics predicts the end of everything meaningful, it forces us to rethink what meaning actually is. When the implications of heat death are pushed beyond physics and into the realm of existence itself, the question becomes unavoidable. What does it mean for life, intelligence, and purpose in a universe that is slowly erasing all structure? This is where heat death stops being only a scientific prediction and becomes a philosophical confrontation with reality. Life exists because the universe is not in equilibrium. Every living system depends on energy flow. Plants convert sunlight into chemical energy. Animals consume stored energy to maintain biological order. Cells constantly fight entropy by exporting waste heat and disorder into their environment. Life is not separate from thermodynamics. It is a temporary local rebellion against entropy, made possible only because the universe as a whole is far from equilibrium. As the universe approaches heat death, this possibility disappears. There will be a point where no environment exists that can support sustained metabolism. No stars to provide energy, no temperature gradients to power chemical reactions, no stable matter structures capable of maintaining complex systems. Life does not lose a battle. The battlefield itself vanishes. This leads to a strange realization. Life is not just fragile, it is time-limited by the structure of the universe. No matter how advanced a civilization becomes, it cannot escape the laws of thermodynamics. Technology can delay extinction, it can improve efficiency, it can harvest energy more cleverly, but it cannot create energy gradients out of nothing. It cannot reverse entropy on a cosmic scale. Even the most advanced civilization imaginable would eventually face the same wall. No usable energy left. This is sometimes called the cosmic energy deadline, not a specific date, but an unavoidable boundary in the future. After this boundary, intelligence cannot persist in any meaningful form. Not because of violence, not because of catastrophe, but because the physical conditions required for thought no longer exist. Thought itself is a physical process. Neurons fire because of electrical gradients. Computers operate because of voltage differences. Information processing always requires energy flow. In a heat-dead universe, there is no flow, no processing, no thinking. This means that intelligence is also temporary. Not just human intelligence, all intelligence. No matter how alien, no matter how advanced, no matter how distributed, all thinking systems eventually face thermal silence. This challenges many science fiction ideas about eternal civilizations or immortal cosmic empires. Physics does not allow infinite survival. At best, it allows delay, prolongation, optimization, but not permanence. Even strategies like moving closer to black holes to extract energy or harvesting background radiation only extend survival marginally compared to cosmic timescales. Eventually, the energy budget runs out, and when it does, intelligence disappears not with a scream, but with quiet inactivity. Another unsettling implication is the fate of knowledge. Knowledge requires storage, libraries, databases, memory structures. All of these rely on stable matter and energy gradients. As matter decays and temperature differences vanish, storage becomes impossible. Even if information is technically conserved at the quantum level, it becomes physically unrecoverable. No medium remains capable of preserving patterns. No observer remains capable of reading them. This means that everything learned by every civilization will eventually vanish. Not destroyed, not burned, not erased violently, simply dissolved into uniform randomness. This includes science, art, history, culture. Every trace of experience becomes thermodynamically irrelevant. This idea is deeply uncomfortable. Humans naturally seek permanence. We build monuments, we archive data, we send messages into space. We hope to leave something behind. Heat death reveals that the universe offers no permanent record. Cosmic time is too vast, entropy too powerful. Nothing physical lasts forever, but this does not necessarily make existence meaningless. It changes the frame. Meaning does not come from permanence, it comes from experience, from process, from participation. Life and intelligence exist during a window of cosmic opportunity, a temporary era where structure is possible. That window is precious precisely because it is finite. Heat death does not erase the fact that the universe once hosted complexity. It only ensures that complexity does not last indefinitely. This leads to a deeper philosophical shift. Instead of viewing existence as a quest for eternal survival, it becomes a story of temporary emergence. The universe creates pockets of order. Those pockets grow, interact, evolve, then dissolve. This pattern is not failure, it is natural evolution. Just as stars are born and die, so too are civilizations. So too is cosmic structure itself. Everything is transient, but transient does not mean meaningless. In fact, transience gives value. If everything were eternal, nothing would be special. Scarcity creates importance. Limited time creates urgency. Finite existence creates significance. Heat death forces this perspective onto the largest possible scale. It shows that the universe itself follows the same pattern as everything inside it: emergence, evolution, decay. Another implication involves the concept of progress. Humans often imagine progress as linear improvement toward a final goal. Heat death shows that cosmic progress has no final destination. There is no ultimate stable civilization state, no perfect equilibrium of prosperity. The universe allows complexity to rise, but does not preserve it indefinitely. Progress exists only within limited windows of favorable conditions. This reframes the purpose of advancement. Technology is not about escaping physics. It is about maximizing the richness of experience within available time. Science is not about achieving immortality. It is about understanding reality while understanding is possible. Civilization becomes a temporary phenomenon, a brief cosmic experiment, but one that can still be meaningful. Another unsettling question arises. If heat death is inevitable, why did the universe start in such a low entropy state at all? Why was the early universe so ordered? Why did it allow stars, galaxies, and life to exist in the first place? Physics does not yet fully answer this. Some theories propose inflation created extreme uniformity. Others suggest deeper cosmological principles. But the origin of low entropy remains one of the greatest unsolved mysteries. This mystery sits at the beginning of the heat death story. The universe began in a special state. It will end in a generic one. Understanding why the beginning was special may reveal deeper laws of reality. This is why heat death is not just about the end. It is also about the beginning. It connects the Big Bang to the far future through thermodynamics. It frames cosmic history as a long journey from order to equilibrium. Another implication involves the emotional response to this knowledge. Some people experience existential anxiety, others experience cosmic awe. Some find motivation, others feel insignificance. All of these reactions are natural. Heat death forces humanity to confront its scale, its fragility, its temporaliness. But it also highlights something extraordinary. Despite living in a universe that will eventually forget everything, conscious beings emerged who can understand this fate. The universe produced observers capable of comprehending its own ending. This is remarkable. It means that during this brief window of cosmic complexity, awareness itself exists. The universe becomes aware of itself through intelligent life. Even if this awareness does not last forever, it exists now. And that existence is not erased by future equilibrium. The experience already happened. Heat death cannot undo the fact that complexity once existed. It only prevents it from continuing indefinitely. Another important reflection is the idea of legacy. If nothing physical lasts forever, what does legacy mean? Legacy becomes relational, not about eternal monuments, but about influence within time. Ideas shape minds. Actions shape societies. Knowledge shapes future discoveries. Even if all of this eventually disappears, it still matters within the era it exists. Meaning does not require infinity. It requires impact. It requires connection. It requires participation in the unfolding of reality. Heat death reframes meaning as local and temporal rather than eternal and cosmic. This perspective can be liberating. It removes the pressure of immortality. It emphasizes the value of present existence. It highlights the importance of what happens now. Another implication is the humility it brings to human ambition. Civilizations often imagine themselves as permanent. Heat death reveals that permanence is an illusion. Everything is temporary, even galaxies, even superclusters, even space-time structure itself. This humility does not diminish achievement, it contextualizes it. It places human effort within a larger cosmic story, one where no single species, civilization, or structure dominates forever. Finally, heat death challenges the deepest assumption humans make about the universe. That existence must have a permanent endpoint of meaning. Physics suggests otherwise. The universe does not guarantee lasting significance. It only guarantees evolution according to law. Meaning, therefore, is something created by conscious beings, not something granted by cosmic destiny. This does not make meaning weaker. It makes it human. It makes it experiential. It makes it real within time. In the next part, we will explore whether any theoretical loopholes exist, exotic physics, multiverse scenarios, or unknown forces that could prevent heat death, reverse entropy, or create new cosmic beginnings. Because even at the edge of thermodynamic finality, science continues to ask the ultimate question: is heat death truly the final ending, or just one chapter in a much larger cosmic story? As the idea of heat death pushes against the limits of imagination, scientists naturally ask whether the universe is truly locked into this fate, or whether there exist hidden mechanisms that could alter the ending. Throughout modern physics, several speculative possibilities have emerged. None are confirmed. None offer guaranteed escape, but each reveals how deeply humanity wants to understand whether cosmic finality is absolute. One of the first concepts often discussed is vacuum decay. According to quantum field theory, the vacuum of space is not empty, it has energy. That energy may exist in different states, much like a ball resting in a valley. The universe might currently occupy a metastable vacuum state, not the lowest possible energy configuration. If this is true, a transition could someday occur. A bubble of lower energy vacuum could spontaneously form and expand at the speed of light. Inside this bubble, the laws of physics would change. Particle masses could shift, forces could behave differently. Atoms might not exist, stars might not form. This would not save the current universe, it would erase it. From the perspective of observers, vacuum decay would look like instant annihilation. No warning, no gradual fade, just a fundamental rewrite of reality. This scenario does not prevent heat death. It replaces it with something even more final. The current universe would not continue. It would be overwritten. Another possibility explored in theoretical physics is quantum recurrence. In certain simplified models, a system with finite energy and volume can, given enough time, return to a state very similar to its original configuration. This is called Poincaré recurrence. Applied to the universe, this suggests that after unimaginable timescales, random fluctuations could reconstruct low-entropy states. But there is a major problem. The universe is expanding. Its volume is increasing. Energy is spreading. This breaks the conditions required for recurrence. Even if recurrence were possible, the timescales would be so vast that they exceed any meaningful physical time frame. Numbers like 10 circumflex 120 years appear, values so enormous they surpass comprehension. Practically speaking, recurrence does not rescue structure. It turns heat death into a statistical waiting room where nothing meaningful happens. Another proposed escape involves cyclic universe models. In these models, the universe undergoes repeated cycles of expansion and contraction. Big bangs follow big crunches. Heat death is avoided because the universe resets. However, current observations strongly contradict this idea. Dark energy is accelerating expansion, not slowing it. The universe is not collapsing, it is speeding up. For a cyclic model to work, unknown physics would be required to reverse expansion. There is currently no evidence such a mechanism exists. While cyclic theories are mathematically interesting, they remain speculative and unsupported by observation. Another idea involves baby universes. Some quantum gravity theories suggest black holes could spawn new universes inside their event horizons. These baby universes would be disconnected from our own. They would not save our universe from heat death. They would simply create new, separate universes elsewhere in the multiverse. From the perspective of this universe, heat death still occurs. Even if new universes are born, continuity is lost. The story of this cosmos still ends. Another possibility is the existence of unknown forms of energy or physics beyond the standard model. Dark energy itself is poorly understood. If its behavior changes over time, it could alter the universe's fate. For example, if dark energy weakened or reversed, expansion might slow, structure might remain bound longer. But even in this case, entropy would still increase. Energy gradients would still fade. The fundamental problem remains. Thermodynamics does not disappear simply because cosmic expansion changes speed. Unless the laws of physics themselves are radically different from what we currently understand, heat death remains the most stable end state. Another speculative idea involves information preservation at the quantum level. Some physicists propose that information might be stored in subtle correlations across space-time. Even in maximum entropy, information may not be destroyed, only encoded in extremely complex entanglement patterns. But this does not restore structure. It does not allow life or intelligence to function. It does not reverse equilibrium. It simply means the universe keeps a mathematical memory that no physical process can access. From a practical standpoint, this changes nothing. Heat death remains a universe without activity, without observers, without experience. Some researchers have explored the idea of using black holes as long-term energy sources. Civilizations could orbit black holes and harvest Hawking radiation. They could slow subjective time through relativistic effects. They could stretch survival across enormous durations. This is theoretically possible, but it is not infinite. Black holes evaporate, energy output declines. Eventually, even this source disappears. Survival can be extended, but not eternal. Even the most advanced imaginable technology cannot violate thermodynamics. Another concept sometimes discussed is cosmic engineering, rearranging stars, moving galaxies, optimizing energy extraction, maximizing efficiency. These strategies could prolong the era of complexity. They could delay the onset of heat death, but they cannot stop it. Entropy production can be slowed, not eliminated. No matter how clever the engineering, the energy budget is finite. The universe contains a limited amount of usable energy. Once it is spread too evenly, no machine can recompress it without spending more energy than it gains. This is a fundamental limit, not a technological problem. Another fascinating idea involves changing the arrow of time. Some speculative physics suggests that under extreme conditions, entropy behavior could change locally, but reversing entropy on cosmic scales would require conditions far beyond what is physically plausible. The arrow of time is deeply rooted in the initial conditions of the universe. It is not something that can be flipped like a switch. Heat death is built into the temporal structure of space-time itself. Another radical idea is that the universe may not be the only one. The multiverse hypothesis suggests that many universes exist with different physical laws. Some of these universes might avoid heat death. Some might be eternal. Some might collapse. Some might cycle. But this does not change the fate of our universe. It only changes the broader cosmic context. From within this universe, heat death remains the predicted outcome. There is no known bridge that allows matter, energy, or observers to escape into another universe. The multiverse offers philosophical perspective, not physical rescue. All of these speculative ideas highlight one important truth. Physics does not currently provide a reliable escape from heat death. Every proposed loophole either destroys the universe, replaces it, or delays the inevitable without preventing it. Heat death remains the most consistent outcome given current understanding. This does not mean science has given up. It means science is honest about limits. It recognizes that some boundaries may be fundamental. The universe may not be designed for permanence. It may be designed for evolution followed by equilibrium. This realization changes the way humanity thinks about cosmic destiny. Instead of dreaming of eternal survival, the focus shifts to meaningful existence within limited time. Instead of seeking infinite extension, attention turns to understanding the universe while it is still structured. Instead of fearing the distant future, emphasis moves to the present era, the only era where complexity thrives. Another implication of this perspective is the recognition that the current cosmic era is special. Stars still shine, galaxies still form, life still exists, structure still evolves. This era will not last forever. It is a brief window in cosmic history, and within this window, intelligence has emerged capable of understanding both the past and the future. This makes the present moment scientifically precious. It is not just another point in time. It is one of the few periods where observation, understanding, and complexity coexist. Heat death gives this era context. It frames it as temporary but extraordinary. Another reflection is the emotional response to inevitability. Some may feel despair, others feel motivation. Knowing that the universe will eventually forget everything can inspire urgency. It can motivate learning, it can encourage exploration. It can shift focus toward experiences, relationships, and discovery. When permanence is removed, presence becomes more valuable. The knowledge of heat death does not remove meaning, it reshapes it. Meaning becomes something created within time, not something guaranteed forever. Finally, heat death teaches humility. It reminds humanity that it is not separate from cosmic law. No civilization escapes physics. No technology bypasses entropy. No intelligence outlasts thermodynamics. The universe is bigger than ambition, stronger than invention, older than memory. Yet within this vast system, consciousness still emerged, still observed, still questioned, still searched for understanding. And that alone is remarkable. In the next part, we will examine the timeline of heat death in even greater detail, from the last star formation to the evaporation of black holes and the final freeze of the cosmos, step by step through the far future of time. Because understanding the end requires understanding the slow, patient march of the universe toward equilibrium. To truly understand heat death, it is not enough to imagine a single distant ending. The universe does not reach equilibrium suddenly. It passes through a series of long, quiet eras, each one marking a gradual loss of structure, energy, and activity. These eras unfold across timescales so immense that even billions of years become small steps in a cosmic countdown. The first major phase is the Stelliferous era, the age we currently live in. This is the era of stars. Galaxies glow, nebulae collapse, planets form, life exists, energy flows freely from nuclear fusion inside stars. This era began roughly 100 million years after the Big Bang and will last for about 10 trillion years. Right now, the universe is only 13.8 billion years old. We are still in the early part of this bright chapter. During this time, stars convert hydrogen into helium and heavier elements. Massive stars live fast and die explosively. Smaller stars burn slowly, conserving fuel over trillions of years. Red dwarf stars, the smallest and most efficient stars, will dominate the far future of this era. Some will shine for up to 10 trillion years. Eventually, however, even red dwarfs exhaust their hydrogen. When the last generation of stars finishes burning, the universe enters the degenerate era. This is the era of stellar remnants. No new stars form. Galaxies become dark collections of white dwarfs, neutron stars, and black holes. Occasionally, rare gravitational interactions may cause stellar remnants to collide or merge, releasing brief flashes of energy. But these events become increasingly rare as expansion separates objects. Most matter settles into slow, quiet orbits. White dwarfs cool into black dwarfs, cold, inert spheres of degenerate matter. Neutron stars lose their radiation and heat. Black holes dominate the gravitational landscape. This era lasts from about 10 trillion years to roughly 10 circumflex 40 years. During this time, structure still exists. Galaxies still have shape. Orbits still occur, but activity steadily declines. Energy becomes harder to extract. Temperature differences fade. The universe becomes colder and quieter. After the degenerate era comes the black hole era. By this point, most ordinary matter has either decayed or fallen into black holes. Black holes become the primary remaining structured objects in the universe. They drift through expanding space. They merge occasionally. They slowly evaporate through Hawking radiation. This evaporation is extraordinarily slow. Small black holes evaporate faster. Large black holes take vastly longer. A black hole with the mass of 1 billion suns could survive for 10 circumflex 100 years. During this era, black holes represent the last concentrated energy reservoirs. They are the final engines of cosmic activity, but even they are temporary. As they evaporate, they release low-energy radiation. The universe becomes increasingly dominated by photons and elementary particles. After the last black hole disappears, the universe enters the dark era, the final stage of heat death. This is the era of near-perfect equilibrium. No stars, no black holes, no galaxies. Only thin particles and stretched radiation moving through expanding space. Temperatures approach absolute zero, energy gradients vanish, structure disappears. At this point, entropy is near its maximum. The universe has reached its thermodynamic endpoint. This timeline shows that heat death is not a single event, it is a process spanning unimaginable durations. Each era removes another layer of complexity. Each transition marks the loss of another source of energy. What makes this process so powerful is that it does not require destruction. It requires only time. Stars burn out because fuel is finite. Black holes evaporate because quantum physics demands it. Expansion continues because space-time geometry dictates it. No intervention is necessary, no catastrophe is required. Heat death is the default trajectory of the universe. Another important aspect of this timeline is the role of expansion. As space expands, galaxies become isolated. Local groups remain gravitationally bound, but distant clusters disappear beyond the cosmic horizon. This isolation accelerates heat death. It prevents energy exchange between regions. It reduces interactions. It traps each region in its own thermodynamic fate. Eventually, every region becomes an island of low-energy particles drifting in vast emptiness. This fragmentation of cosmic structure removes any possibility of large-scale recovery. There is no global system left, only isolated pockets of near equilibrium. Another crucial detail is the behavior of temperature. Temperature is not just a measure of heat. It reflects average energy per particle. As the universe expands, energy density drops, radiation redshifts, particles slow down, temperature approaches absolute zero, but absolute zero is never fully reached. Quantum mechanics prevents complete stillness. There is always some minimal motion. However, this residual energy is not useful. It cannot drive work. It cannot create structure. It is random, isotropic motion. This reinforces the idea that heat death is not coldness alone, it is uniformity. It is the loss of contrast. Another aspect of the timeline involves proton decay. By gravity, if protons decay, then during the degenerate era, ordinary matter slowly dissolves into radiation. White dwarfs and neutron stars would gradually disintegrate. Atoms would no longer exist. Matter itself would fade. This would accelerate the approach to heat death. While proton decay has not yet been observed, many theoretical models predict it. If confirmed, it strengthens the heat death scenario even further. Another detail involves neutrinos. These ghost-like particles interact extremely weakly with matter. Over time, neutrinos dominate the particle population of the universe. They drift freely through space, carrying energy that cannot be efficiently used. This contributes to the thinning of usable energy. Another subtle aspect is the fate of atomic nuclei. Over extremely long timescales, quantum tunneling could cause even stable atomic configurations to decay. This is not fully understood, but it suggests that nothing remains perfectly stable forever. Everything eventually transforms. Another important timeline component is the disappearance of structure itself. As expansion continues, gravitationally bound systems become increasingly isolated. Galaxies lose intergalactic connections. Filaments thin out. The cosmic web dissolves. What remains is a nearly uniform distribution of low-energy particles. Structure disappears not because it collapses, but because it stretches until it no longer matters. This stretching of space is crucial. It ensures that even if matter remains, it becomes too sparse to interact. Distance itself becomes a barrier. Another reflection on the timeline is how it reshapes the concept of far future. Human imagination often struggles with millions of years. Heat death involves timescales of trillions, quadrillions, and far beyond. These numbers have no intuitive meaning. They exceed the age of stars, galaxies, and even the cosmic web. They represent a regime where the universe exists longer in decay than it ever existed in complexity. This is one of the most profound realizations. The universe spends most of its lifespan in near equilibrium. The era of stars and life is brief by comparison. This makes the present epoch extraordinarily rare in cosmic history. We live during the brightest, most active period of the universe. This rarity gives the present moment significance. It is not typical. It is special. It is a short-lived window where complexity thrives. Another implication of the timeline is that the universe's future is simpler than its past. The Big Bang produced extreme complexity potential. Structure grew. Heat death removes that complexity. The universe trends towards simplicity, uniformity, minimal variation. This is the opposite of what many expect. Progress in human society often means increased complexity. The universe does not follow this pattern forever. It builds complexity temporarily, then dissolves it. This challenges intuitive ideas about cosmic progress. The universe does not aim toward greater organization, it aims toward equilibrium. Finally, understanding this timeline forces a new perspective on cosmic existence. The universe is not designed to host eternal civilizations, it is designed to evolve according to physical law. Life appears as a temporary phenomenon enabled by favorable conditions. When those conditions vanish, life vanishes, not because of malice, not because of failure, but because the universe moved toward its natural thermodynamic state. In the next part, we will explore the most extreme theoretical ideas about the final moments of the universe, what the last particles experience, whether quantum fluctuations could still occur, and what nothingness actually looks like in a heat-dead cosmos. Because when everything fades, the final question becomes, what remains when there is nothing left to change? As the universe approaches its final thermodynamic state, the concept of nothingness becomes increasingly difficult to define. Heat death does not produce an empty void. It produces something far stranger, a universe that still exists, still contains particles and energy, but has lost the ability to change in any meaningful way. Understanding this final condition requires stepping beyond ordinary intuition and into the deepest layers of physics. In a heat-dead universe, space is filled with extremely low-energy radiation. Photons still exist. Neutrinos still drift. Exotic particles may still appear briefly through quantum fluctuations, but everything is spread so evenly that no region differs significantly from any other. There is no preferred direction, no hot spot, no cold zone, no gravitational basin capable of collecting matter. Uniformity becomes absolute. This uniformity eliminates structure. Galaxies require density contrasts. Stars require compressed gas. Planets require gravitational collapse. None of these can occur in equilibrium. Even atomic bonds become unstable if matter thins sufficiently and temperatures approach absolute zero. What remains is a diffuse cosmic background of near motionless particles. From a distance, this universe would appear almost perfectly dark, not because photons do not exist, but because they are so stretched that their wavelengths exceed the scale of observable space. They carry almost no energy. They no longer interact with matter. They are present, but irrelevant. In this final stage, the concept of temperature becomes meaningless. Temperature measures average kinetic energy. When energy differences vanish, temperature loses operational meaning. Every region has nearly identical energy density. There is no thermal flow, no heat exchange, no cooling, no warming. Everything simply exists at the same baseline state. This raises a strange question. If nothing changes, does the universe still happen? From a physical perspective, time continues as a parameter in equations, but from an experiential perspective, time ceases to exist. No clocks tick, no processes unfold, no events occur. A universe with no events is indistinguishable from a frozen moment. This creates a kind of eternal present, not a dramatic eternity, but a static one, without narrative, without progression, without development. From the perspective of physics, the universe has reached its final solution. The equations are satisfied, entropy is maximized. There is no remaining potential energy to convert into work. This is the ultimate equilibrium state. Yet quantum mechanics adds a layer of subtle complexity. Even in perfect equilibrium, quantum fluctuations may still occur. Particles can briefly appear and disappear. Energy can fluctuate within uncertainty limits. But these fluctuations are extremely small. They do not produce sustained structure. They do not accumulate. They do not lead to new galaxies or stars. They are random noise in an otherwise silent universe. This noise does not restore time. It does not restore history. It only produces momentary disturbances that vanish immediately. Another strange phenomenon that could theoretically occur in a heat-dead universe is the spontaneous appearance of complex structures through random fluctuations. In infinite time, even extremely improbable events become possible. This leads to ideas such as Boltzmann brains, hypothetical self-aware systems that arise purely by chance from random particle arrangements. However, these would be extraordinarily rare. They would exist briefly. They would have no environment, no history, no continuity, no society. They would not rebuild the universe. They would be isolated flashes of awareness in a sea of nothingness. This highlights the emptiness of the heat-dead cosmos. When the most optimistic possibility is a random hallucination of consciousness, the depth of equilibrium becomes clear. Another implication concerns gravity. In a universe with extremely low matter density, gravity becomes almost irrelevant. Particles are too far apart to attract significantly. Even if gravitational attraction exists, expansion dominates. Space grows faster than matter can cluster. This prevents any new structures from forming. Gravity becomes a weak background force with no ability to shape the universe. This marks the final defeat of structure-forming forces. The cosmic web dissolves, filaments disappear, clusters disperse, only uniformity remains. Another aspect of the final state is the fate of space itself. Some theories suggest that space-time may continue expanding forever. Others propose it may approach a constant expansion rate. Either way, the geometry of space becomes increasingly flat and empty. Distances between particles grow larger, interactions become rarer, space becomes dominant over matter. The universe becomes more about emptiness than content. This emptiness is not absolute nothingness. It is a structured vacuum filled with quantum fields. But these fields remain in their lowest energy states. No large-scale excitations occur. No significant processes unfold. The universe becomes a quiet quantum background. Another profound implication of this final state is the loss of reference frames. Without objects, motion loses meaning. Velocity becomes irrelevant when nothing interacts. Position becomes meaningless when everything is uniform. Even the idea of here and there loses significance. Space becomes homogeneous. All points become equivalent. This erases the concept of location. The universe becomes locationless in any meaningful sense. Another unsettling detail is the disappearance of causality. Causality depends on sequences of events. When events stop occurring, cause and effect lose relevance. Physics becomes static. The universe stops telling stories. It stops producing outcomes. It stops generating change. This is not death in the biological sense. It is cessation of becoming. Reality no longer evolves. It simply exists. From a philosophical perspective, this is the ultimate end of history. Not just human history, cosmic history. The chain of events that began with the Big Bang finally reaches a point where no new chapters can be written. The universe does not conclude with a final dramatic scene. It fades into silence. Another dimension of this final state is the fate of observation. Observation requires interaction, photons interacting with matter, particles scattering, signals traveling. In a heat-dead universe, observation becomes impossible. There are no observers, but even if something could observe, there would be nothing to observe. Everything looks the same everywhere. No contrast, no information, no signal. The universe becomes unobservable even to itself. This is a strange concept, a universe that exists but cannot be perceived, not because it is hidden, but because it contains no distinguishable features. Another implication concerns the arrow of time. The arrow of time is driven by entropy increase. When entropy reaches maximum, the arrow disappears. Time becomes symmetric. Past and future become indistinguishable. There is no direction, no flow. This is the ultimate flattening of temporal structure. Time loses its asymmetry. The universe becomes temporally static. This challenges human understanding. We experience time as constant change. A universe without change defies everyday intuition. It exists outside experience. Another reflection is the idea that heat death is not end in the emotional sense. It is not tragedy. It is not catastrophe. It is completion. The universe follows its thermodynamic path to equilibrium. From a physical perspective, this is the most natural outcome. From a human perspective, it feels empty. But emptiness is not inherently negative in physics. It is simply a state of minimal energy and maximum stability. The universe becomes perfectly stable. Nothing can disturb it. Nothing can evolve. It is final. And yet, this final state does not erase the past. Everything that ever existed still existed. Every star burned. Every civilization lived. Every moment occurred. Heat death does not undo history. It only prevents new history from forming. This distinction is important. The universe is not erased. It is frozen. Another implication is the role of scale. Heat death occurs over unimaginable time, long after any conceivable civilization disappears, long after galaxies fade, long after black holes evaporate. This makes it irrelevant to short-term concerns, but it remains fundamental to cosmic understanding. It defines the ultimate boundary of physical possibility. It shows where all paths lead. Finally, heat death forces humanity to confront the ultimate question. If everything eventually becomes still, what is the value of motion now? The answer lies not in eternity. It lies in participation, in experience, in understanding, in creation. The universe allows complexity for a limited time. We exist during that time. We can observe. We can learn. We can create meaning. That window is precious, not because it lasts forever, but because it does not. In the next part, we will explore how heat death changes the way we think about the present universe, why this knowledge matters today, how it reshapes scientific priorities, and what it tells us about our role in a cosmos that is slowly running out of time. Because understanding the end forces us to reevaluate the beginning. When the ultimate fate of the universe is placed into perspective, something unexpected happens. Heat death does not only describe the far future, it reshapes how the present moment is understood. Knowing that all structure will eventually fade gives new meaning to the era of complexity we currently inhabit. It transforms today's universe into something rare, fragile, and extraordinary. Right now, the cosmos is alive with activity. Stars ignite and explode, galaxies collide and merge, planets form, life evolves. Information flows. From a cosmic perspective, this era is temporary. It is a brief window between two extremes. On one side lies the smooth, uniform early universe before structure fully formed. On the other side lies the heat-dead future where structure has vanished. We live in the narrow middle, the only period where complexity thrives. This makes the present epoch cosmically special, not because it is central, but because it is rare. For most of the universe's lifespan, stars will not shine, life will not exist, structure will not evolve. The age of galaxies and life occupies only a thin slice of cosmic time. This realization changes the way cosmologists view observation. We are not just studying the universe, we are studying a fleeting phase of its evolution. Future observers, if they exist at all, will not see the same sky. They will not detect distant galaxies. They will not observe cosmic background radiation. They will not witness the large-scale structure of the universe. The evidence available today will vanish with expansion and time. This makes present-day cosmology uniquely privileged. It is one of the few eras when the universe can be fully studied. Another important consequence of heat death is the way it reframes scientific priorities. Understanding cosmic evolution becomes more urgent. Mapping galaxies, studying dark energy, investigating fundamental forces. All of these efforts capture information about the universe before it becomes inaccessible. Science becomes not only discovery, but preservation. Preservation of cosmic history, preservation of knowledge, preservation of understanding. The universe will not remember itself, but intelligent beings can, at least for a time. This gives scientific research a deeper significance. It is not only about curiosity, it is about documenting reality during its most informative phase. Another implication is how heat death reshapes the concept of progress. In everyday thinking, progress implies continuous improvement, but cosmology reveals a different pattern. The universe does not improve indefinitely. It evolves. It grows more complex for a time, then it becomes simpler again. Complexity is not permanent. It is transitional. This does not invalidate progress. It redefines it. Progress becomes about deepening understanding within limited time, not achieving eternal perfection. It becomes about maximizing knowledge and experience while conditions allow it. Another perspective emerges when considering technological civilization. Advanced civilizations may dream of interstellar expansion, galactic engineering, and cosmic dominance. Heat death places a limit on all such ambitions. There is no permanent empire, no eternal expansion, no infinite growth. Even if a civilization spreads across galaxies, the energy available to sustain it declines. Expansion cannot outrun thermodynamics. This forces a shift in values. Instead of infinite accumulation, the focus becomes efficiency, optimization, sustainability, meaningful use of limited resources. Heat death encourages a long-term perspective, not one based on endless growth, but one based on stewardship of the present. Another implication concerns the nature of observation. Observing the universe today is possible because photons from distant galaxies can still reach Earth. As expansion accelerates, this window closes. Distant galaxies fade beyond the cosmic horizon. Signals become too stretched to detect. Eventually, only the local group remains visible. The universe becomes observationally small. This means that future civilizations may have a radically different understanding of cosmology. They may not know about the Big Bang. They may not detect cosmic expansion. They may believe they live in a static, isolated universe. Heat death thus creates an information asymmetry across time. The present generation has access to cosmic data that future generations may never see. This gives current knowledge historical value. It is not just accurate, it is time-sensitive. Another important consequence is the way heat death influences philosophical thinking. It forces a confrontation with finitude, not just human finitude, cosmic finitude. The universe itself has a life cycle. It is not eternal in a meaningful sense. It has a beginning. It has an evolution. It has an end state. This challenges ancient ideas of an unchanging cosmos. It replaces them with a dynamic, evolving universe, one that has a story, one that progresses through phases, one that eventually reaches a final equilibrium. This narrative structure gives cosmology a new depth. It becomes a story of birth, growth, aging, and stillness. Another implication involves the concept of value. If everything eventually disappears, why does anything matter? From a physical perspective, the universe does not assign value. Value is created by conscious systems. Heat death does not remove value from experiences that occur. It only limits their duration. A sunset does not become meaningless because night follows. A life does not become meaningless because it ends. Meaning is tied to experience, not permanence. Heat death reinforces this principle on a cosmic scale. It shows that temporary existence can still be significant. In fact, its temporariness is what gives it weight. Another important perspective is the emotional response heat death evokes. For some, it creates existential dread. For others, it inspires awe. For others, it brings clarity. There is no single correct reaction, but it undeniably expands perspective. It forces individuals to think beyond personal timelines, beyond cultural history, beyond planetary existence. It encourages cosmic humility. It places human concerns within a much larger framework. This can be grounding. It can reduce the perceived magnitude of everyday conflicts. It can shift attention toward broader questions. Another implication is the effect on environmental thinking. Knowing that the universe has limited complexity time does not excuse environmental destruction. It does the opposite. It emphasizes the rarity of life-supporting conditions. Earth exists within a narrow habitable window. That window is part of a larger cosmic window of complexity. Protecting planetary ecosystems becomes more meaningful when viewed in this context. Life is rare. Complexity is temporary. Preserving it matters. Another perspective emerges when considering art and culture. Human creativity exists during a brief cosmic moment. Art, music, literature, and science are expressions of complexity. They are part of the universe exploring itself. Heat death does not erase the fact that creativity existed. It simply sets a limit on how long it can continue. This adds emotional depth to human cultural activity. It becomes part of a larger cosmic narrative. Another implication is how heat death reshapes the idea of legacy. Legacy is not about eternal survival. It is about influence within time. What we create affects others. What we learn informs future generations. What we build shapes civilization. Even if everything eventually fades, these effects still occur. They still matter in their time. Heat death encourages a shift from eternal thinking to temporal responsibility. Another important reflection is the role of curiosity. The universe will not preserve complexity forever, but it allows conscious beings to explore it while it exists. Curiosity becomes a fundamental response to this opportunity. Studying the universe is not just intellectual, it is participation in a rare phase of cosmic evolution. Another implication concerns the emotional resilience of humanity. Confronting heat death does not require despair. It can inspire gratitude. Gratitude for existence, for complexity, for consciousness, for the ability to understand the universe. We exist during a remarkable period. We can observe galaxies. We can understand stars. We can predict cosmic endings. This ability is extraordinary. Finally, heat death changes the way the present is experienced. The night sky becomes more than beautiful, it becomes temporary. The stars become more than distant lights, they become fleeting. The universe becomes not just vast, but fragile in its complexity. This fragility makes the present moment more meaningful, not less, because it will not last forever. In the next part, we will examine how scientists attempt to measure the approach toward heat death, how entropy is tracked, how cosmic expansion is quantified, and how researchers use data to predict the universe's long-term fate. Because heat death is not just theory, it is a measurable direction written into the fabric of reality. Understanding heat death is not only a philosophical exercise, it is grounded in measurable physical quantities. Scientists do not simply imagine the universe drifting toward equilibrium, they observe the processes that drive it. Expansion, entropy growth, energy loss, and cosmic cooling are not abstract ideas. They are recorded in data, written into radiation, and visible in the large-scale behavior of space itself. One of the most important measurements related to heat death is cosmic expansion. Since Edwin Hubble first observed that distant galaxies are moving away from us, astronomers have measured the expansion rate of the universe with increasing precision. This expansion is not slowing down, it is accelerating. This acceleration is driven by dark energy, a mysterious form of energy that permeates space and pushes galaxies apart. As expansion accelerates, it directly contributes to heat death. Distances grow. Matter becomes more isolated. Energy density decreases. Interactions become rarer. This is not speculation. It is directly observed through supernova measurements, galaxy surveys, and cosmic background radiation. The faster space expands, the faster the universe approaches a state where large-scale structure becomes impossible. Another critical measurement is the cosmic microwave background. This faint radiation is the afterglow of the Big Bang. It fills the universe uniformly and carries information about the early state of cosmic entropy. The cosmic microwave background has an extremely precise temperature of about 2.7 Kelvin above absolute zero. Over time, this temperature continues to drop as space expands and photons redshift. This cooling trend is a direct indicator of entropy evolution. It shows the universe moving toward lower energy density and greater uniformity. By measuring this radiation with high accuracy, scientists can reconstruct the thermal history of the universe and project its future behavior. Another measurable factor is stellar evolution. Astronomers track star formation rates across cosmic time. They observed that star formation peaked billions of years ago and has been declining ever since. Galaxies today form far fewer stars than they did in the past. Gas supplies are shrinking. Cold molecular clouds are becoming rarer. This decline confirms that the era of active star formation is finite. It supports predictions that new stars will eventually stop forming altogether. This directly feeds into the heat death timeline. Another observable driver of heat death is black hole evaporation. Although Hawking radiation has not yet been directly observed due to its extreme weakness, it is a robust prediction of quantum field theory in curved spacetime. Theoretical models show that black holes must lose mass over time. This process is slow but unavoidable. The existence of Hawking radiation is supported indirectly through consistency with thermodynamics and quantum mechanics. If black holes did not evaporate, they would violate fundamental physical principles. Thus, even the most extreme energy storage systems in the universe are temporary. Another measurable component is entropy production. Entropy is not directly visible, but its effects are. Every time energy spreads out, entropy increases. Stars produce entropy by converting nuclear fuel into radiation. Galaxies produce entropy through collisions and gravitational interactions. Cosmic expansion itself increases entropy by spreading energy across larger volumes. Scientists can estimate entropy budgets by tracking radiation output, matter distribution, and thermal processes. These estimates show that the total entropy of the universe is steadily increasing. There is no observed mechanism that reduces entropy on a cosmic scale. Local decreases in entropy, such as life or star formation, always require greater increases elsewhere. This confirms the global thermodynamic arrow of time. Another important observation involves large-scale structure evolution. Surveys of galaxies across different distances allow scientists to observe the universe at different ages. This reveals how cosmic structure has grown and stabilized. In the early universe, matter was more uniformly distributed. Over time, gravity created filaments, clusters, and voids. Today, structure formation is slowing. Expansion is outpacing gravitational collapse on large scales. This shift marks the beginning of structural stagnation. The cosmic web is no longer growing significantly. It is gradually freezing into its current form. This observational evidence supports predictions that large-scale structure will eventually stop evolving. Another measurable indicator is energy density decline. As the universe expands, the average energy density drops. Radiation loses energy through redshift. Matter becomes more sparse. This can be measured through cosmic background radiation, galaxy distributions, and gravitational lensing. These measurements show a consistent trend. Energy is becoming less concentrated. This directly aligns with the thermodynamic trajectory toward equilibrium. Another critical factor is particle physics stability. Experiments attempt to detect proton decay and other rare particle processes. While proton decay has not yet been observed, upper limits on its lifetime provide constraints on how long matter can remain stable. If proton decay occurs, it accelerates the loss of structure. Even if it does not, other quantum processes still degrade matter over extreme timescales. These experiments connect microscopic physics with cosmic destiny. They show that the fate of the universe is tied to the behavior of the smallest particles. Another measurable aspect involves neutrino backgrounds. Neutrinos carry energy across cosmic distances and contribute to entropy. They are extremely difficult to detect, but experiments have confirmed their abundance and behavior. Neutrino cooling is another pathway through which energy spreads and becomes unusable. Over time, neutrinos become one of the dominant energy carriers in the universe. They drift freely and interact weakly, making their energy difficult to harness. Another important measurement is the cosmological constant. Dark energy strength determines the long-term expansion behavior of the universe. If dark energy remains constant or increases, expansion continues indefinitely. Current observations strongly support this scenario. This makes heat death the most likely outcome. If dark energy were to weaken or reverse, the future might change, but there is currently no evidence of such behavior. All data points toward continued acceleration. Another aspect of heat death measurement involves gravitational entropy. Gravity behaves differently from other forces. When matter clumps under gravity, entropy can increase even as structure forms. This is counterintuitive, but it plays a crucial role in cosmic evolution. Black holes represent the highest entropy objects in the universe. Their existence shows that entropy is not simply about disorder, it is about the number of possible configurations. As black holes evaporate, this gravitational entropy is released into radiation. This further contributes to equilibrium. Scientists calculate black hole entropy using the Bekenstein-Hawking formula. These calculations reveal that black holes dominate the entropy budget of the universe. This reinforces the importance of black hole evaporation in the heat death timeline. Another measurable process is cosmic background neutrino cooling. Just like the microwave background, neutrinos form a background radiation field. As the universe expands, this background cools and spreads. It represents another reservoir of low-grade energy that becomes increasingly irrelevant for structure formation. Another observational constraint comes from cosmic age estimates. By measuring the expansion rate and cosmic background radiation, scientists determine the universe's age. These measurements allow projections into the future. They show how long stars will burn, how long galaxies remain visible, how long black holes persist. The timeline of heat death is not guesswork. It is built from observed trends extrapolated forward. Another important point is the role of uncertainty. While exact timescales are uncertain, the direction is not. Whether heat death occurs in 10 circumflex 100 years or 10 circumflex 120 years does not change the fundamental outcome. Entropy increases, energy spreads, structure fades. The details may vary. The destination remains the same. Another measurable indicator is cosmic temperature gradients. Today, there are hot stars and cold space. Over time, these gradients shrink. Measurements show the average cosmic temperature decreasing. This trend will continue. Eventually, all temperatures converge. This convergence marks the approach to equilibrium. Another important observation involves intergalactic gas temperature. As galaxies become isolated and star formation stops, intergalactic gas cools and thins. This gas once served as the raw material for stars. Its decline marks the end of cosmic recycling. Measurements of gas density and temperature support this long-term cooling trend. Another scientific tool used to study heat death is computer simulation. Large-scale cosmological simulations model galaxy evolution, dark matter distribution, and expansion. These simulations consistently produce outcomes where structure formation slows and entropy increases. They do not produce spontaneous large-scale reversals. They reinforce the theoretical predictions. Another factor is cosmic horizon growth. As expansion accelerates, the observable universe shrinks in practical terms. The horizon beyond which light can never reach us grows closer. This limits future observation and interaction. Measurements of cosmic horizon behavior confirm this effect. It is another sign of increasing isolation and entropy. Together, these observations create a consistent picture. Heat death is not speculative fantasy. It is supported by expansion data, thermodynamics, stellar evolution, black hole physics, and particle experiments. Each field independently points toward the same long-term outcome. The universe is moving toward equilibrium. This does not make the present meaningless. It makes it scientifically extraordinary. We exist at a time when the universe is still dynamic, still observable, still rich with structure, still capable of producing complexity. Understanding heat death does not remove wonder. It deepens it. It reveals that this era is rare, that the sky we see today is temporary, that the universe is offering a limited window of discovery. In the next part, we will explore how heat death challenges human intuition about endings, why it feels more unsettling than explosions or collapses, and what it teaches about the nature of finality in a universe governed by slow, patient physical laws. Because sometimes the quiet endings are the most profound. When people imagine the end of the universe, they rarely picture heat death. Instead, they imagine fire, collapse, explosion, or sudden annihilation. These dramatic endings feel intuitive because human experience is shaped by visible destruction. Buildings collapse, stars explode, storms arrive suddenly, but heat death is different. It is not violent. It is not fast. It is not cinematic. And that is precisely why it is so unsettling. Heat death represents an ending without spectacle, no final explosion, no universal blackout, no moment when everything suddenly stops. Instead, the universe simply slows. Processes become weaker. Energy spreads thinner, change becomes rarer, motion fades. There is no single moment where the universe dies. There is only a gradual loss of the conditions that allow anything meaningful to happen. This challenges the way humans naturally think about endings. We expect closure. We expect events. Heat death offers neither. This psychological discomfort reveals something deeper about human perception. Humans understand time through events: birth, growth, conflict, resolution. Stories have beginnings and endings because they contain action. Heat death removes action itself. Without events, there is no story. The universe does not conclude with a final chapter. It simply stops producing chapters. From a narrative perspective, this feels incomplete, but from a physical perspective, it is perfectly consistent. The laws of thermodynamics do not promise drama, they promise equilibrium. Another reason heat death feels unsettling is because it removes agency. In catastrophic scenarios like cosmic collapse or vacuum decay, something happens to the universe. There is a cause, there is an event, there is a trigger. In heat death, there is no villain, no cosmic disaster, no singular cause. The universe is not destroyed by something external. It ends itself quietly by following its own rules. Entropy increases because entropy always increases. Expansion continues because expansion is built into space-time. Stars fade because fuel runs out. Nothing attacks the universe. Nothing sabotages it. It simply completes its natural trajectory. This lack of external cause makes heat death feel inevitable in a deeper way than other scenarios. There is nothing to fight against. No intervention. No resistance. The universe is not defeated. It finishes. Another unsettling aspect is the slow scale of the process. Heat death unfolds over timescales so large that they defy emotional comprehension. Millions of years already feel abstract. Trillions of years break intuition. Numbers like 10 circumflex 100 years exist outside normal cognition. Because the process is so slow, there is no sense of urgency within the universe itself. Nothing panics, nothing rushes. The cosmos drifts calmly toward equilibrium. This calmness contrasts sharply with human fear of endings. We associate endings with intensity. Heat death is the opposite. It is the quiet draining of possibility. Another deeply unsettling feature is the way heat death erases contrast. Contrast is fundamental to perception. Light and dark, hot and cold, fast and slow, high and low. Without contrast, nothing stands out. In a heat-dead universe, contrast disappears. Everything becomes nearly the same everywhere. No bright stars against dark space, no hot cores and cold voids, no dense clusters and empty regions. Uniformity replaces diversity. This uniformity removes not only structure but identity. Objects are defined by difference. A star is different from empty space. A galaxy is different from a void. When differences fade, individuality fades. The universe becomes anonymous, featureless, indistinguishable. This loss of identity is psychologically disturbing because human minds rely on difference to recognize reality. Another unsettling implication is the disappearance of direction. Direction requires gradients. Heat flows from hot to cold. Objects fall from high to low gravitational potential. Time flows forward because entropy increases. When gradients disappear, direction disappears. Motion loses purpose. Change loses orientation. The universe becomes directionless. Not just in space, but in time. This removes the intuitive sense of progress or movement forward. There is no forward, there is only equilibrium. Another uncomfortable realization is that heat death does not spare anything special. Not stars, not black holes, not galaxies, not information, not memory, not intelligence. There is no hierarchy of importance. Everything is treated equally by entropy. The most massive structures dissolve just as surely as the smallest particles spread out. Nothing is protected. Nothing is preserved. Nothing is prioritized. This universality makes heat death feel impartial and absolute. There is no exception clause in physics. Another unsettling aspect is that heat death does not violate physical law. It is not a glitch. It is not a breakdown. It is the natural consequence of the same laws that allow stars to shine and life to exist. The same thermodynamics that power engines, metabolism, and sunlight also guarantee eventual equilibrium. This creates a strange paradox. The laws that make complexity possible also ensure that complexity cannot last forever. Creation and destruction are linked by the same rules. This dual role of physics is deeply unsettling because it removes the idea of a separate ending force. The universe does not need a destroyer. Its own structure guarantees its eventual stillness. Another dimension of discomfort comes from the fate of memory. Memory gives continuity to experience. It connects past to present. It allows learning. It creates identity. Heat death erases the physical conditions required for memory, not only biological memory, but all forms of information storage. This means the universe will eventually become a place with no record of its own past. The story of stars, galaxies, and life becomes physically inaccessible. This erasure is not dramatic, it is quiet. The universe does not mourn its own history, it simply loses the ability to remember. This challenges human attachment to legacy. Humans often seek to leave permanent marks, monuments, archives, records. Heat death shows that permanence is not guaranteed at the cosmic level. Everything eventually dissolves into thermal noise. Another unsettling implication is the idea of an eternal future with nothing happening. Infinity is difficult to imagine, but heat death suggests an infinite future where nothing changes, an endless stretch of uniformity, no events, no novelty, no emergence. This is not nothingness. It is worse than nothingness from a human perspective. It is existence without experience, presence without process, being without becoming. For creatures adapted to change, this concept feels alien and uncomfortable. Another psychological tension comes from the contrast between the universe's energetic past and its quiet future. The early universe was violent, dense, dynamic. Stars exploded, galaxies collided, matter reorganized constantly. Heat death is the opposite, cold, sparse, still. The universe transitions from extreme activity to extreme inactivity. This dramatic contrast amplifies the sense of loss. It feels like a fading echo of cosmic vitality. Another unsettling aspect is that heat death removes the possibility of surprise. Surprise requires change, unexpected events, new configurations. In equilibrium, nothing unexpected happens. Random fluctuations may occur, but they do not accumulate into meaningful novelty. The universe becomes predictable in the most extreme way possible. Nothing happens. This removes the sense of discovery. No new stars to observe, no new structures to map, no new phenomena to study. Science itself becomes impossible. Another implication is the loss of complexity. Complexity is one of the universe's most remarkable features. From simple particles emerge atoms, from atoms emerge molecules, from molecules emerge life, from life emerges intelligence. Heat death reverses this trajectory, complexity dissolves. Structure collapses into uniformity, the universe simplifies itself. This simplification is not destructive in the violent sense, it is subtractive. Layer by layer, features disappear, until only the simplest possible configuration remains. Another unsettling detail is the idea that the universe becomes maximally boring, not in an emotional sense, because there are no observers, but in a physical sense. No variation, no dynamics, no patterns. It becomes the most statistically probable state, which is also the least interesting. This challenges human expectations that the universe should remain dramatic or complex. Physics does not guarantee excitement, it guarantees stability. Another psychological challenge is that heat death makes the present feel fragile. Knowing that stars will eventually fade makes current cosmic beauty feel temporary. The night sky becomes precious because it will not always exist. This awareness can create melancholy, but it can also create appreciation. The same knowledge that makes the future bleak makes the present extraordinary. Another unsettling aspect is that heat death does not require catastrophe to reach. There is no final warning, no cosmic siren. The universe does not announce its approach to equilibrium. It simply drifts, silently, slowly, relentlessly. This lack of drama makes the ending feel invisible, which makes it harder to emotionally process. Another layer of discomfort is the idea that everything meaningful happens early. The universe front-loads its complexity. Stars form early, Galaxies peak early, life emerges early. Most of cosmic time is spent in decline. This creates a strange imbalance. The richest era of cosmic activity occupies a small fraction of time. The longest era is emptiness. This challenges intuitive notions of fairness or balance. The universe does not distribute complexity evenly across time. It concentrates it and then dissipates it. Finally, heat death forces humanity to confront the deepest existential question. If everything ends quietly, without drama, without memory, without legacy, what is the point of existence? Physics does not answer this, but it reframes it. Meaning is not something guaranteed by eternity. It is something created during the brief window of complexity. Heat death does not remove meaning, it removes permanence. Meaning becomes local, temporary, experiential, and that does not make it weaker, it makes it real. In the next part, we will explore how humanity emotionally and culturally responds to this knowledge, how art, philosophy, and science reinterpret existence when the universe itself has an expiration date. Because when the cosmos is temporary, the question is no longer how do we last forever, it becomes how do we exist well while we can. As the long journey toward heat death comes into full perspective, one final realization emerges with clarity. The universe is not defined by how it ends, but by how it unfolds. The concept of heat death is not merely a prediction of stillness, it is a framework that reshapes how existence itself is understood. It reveals that the universe is a process, not a static object, a transformation, not a frozen structure. From the moment of the Big Bang, the universe has been in motion. Energy expanded, space stretched, matter condensed, stars ignited, life emerged. All of this occurred because the universe began far from equilibrium. Heat death is not the opposite of creation, it is its continuation. It is the final stage of a thermodynamic journey that began with extreme order. This perspective dissolves the idea of a tragic ending. There is no villain in this story, no collapse caused by failure, no destruction triggered by error. The universe simply follows the consequences of its initial conditions and physical laws. This makes heat death less of a catastrophe and more of a conclusion, a natural closure to a long narrative. Another important insight is the relationship between existence and rarity. The universe's most dynamic phase, the era of stars, galaxies, and life, occupies only a small fraction of cosmic time, yet it is the phase that matters most to conscious beings, not because it lasts longest, but because it contains experience, it contains observation, it contains awareness. From this perspective, duration is not the measure of value, presence is. Intensity of complexity is, richness of interaction is. Heat death teaches that value is not distributed evenly across time, it is concentrated. This concentration makes the present era special, not privileged, but rare. Another insight involves the idea of cosmic opportunity. The universe allows a window in which complexity flourishes. Within that window, intelligence arises, technology develops, knowledge accumulates. This opportunity is not infinite, but it is sufficient. The fact that the universe provides any such window at all is remarkable. Many possible universes might never allow stars to form, might never allow chemistry, might never allow life. Our universe does. For a limited time. Heat death highlights how unusual this is. Another important realization concerns the relationship between physics and meaning. Physics describes how the universe evolves. It does not prescribe purpose. Heat death does not declare existence meaningless. It removes the illusion of cosmic permanence. Meaning becomes something created by conscious systems within time, not something embedded eternally in the fabric of space. This shifts responsibility. Meaning is not given, it is constructed through relationships, through creativity, through understanding. through participation in existence. Another key insight is the role of observation in cosmic history. The universe existed for billions of years before any observers appeared. It will exist for trillions of years after observers disappear. But during the brief period when observation is possible, the universe becomes aware of itself. This is a unique phase. It is not guaranteed, it is not permanent, but it is real. Heat death does not negate this self-awareness. It frames it as a rare event in cosmic history. Another realization is that knowledge itself becomes precious. Understanding the universe is not just intellectual, it is preservation. Once cosmic background radiation fades, once galaxies disappear beyond the horizon, future observers will lack access to fundamental evidence about the universe's origin. The knowledge gathered today is irreplaceable. It captures a moment in cosmic history that will not repeat. Heat death gives scientific discovery a sense of urgency and significance. Another insight involves humility. Heat death places humanity in context. It reminds us that no civilization is permanent, no species is eternal, no technology escapes thermodynamics. This does not diminish human achievements. It grounds them. It encourages responsibility. It discourages arrogance. It invites cooperation rather than domination. Another realization is the connection between creativity and impermanence. Art, science, culture, and innovation exist because time is limited. Scarcity creates motivation. Finite existence gives urgency. Heat death reinforces this relationship. It shows that the universe itself is temporary in its complex phase. Creativity flourishes in the presence of limits, not in infinite stability. Another important reflection is the idea of cosmic gratitude. The universe does not owe complexity. It does not owe life. It does not owe consciousness. Yet it produces them. This creates an opportunity for appreciation, not in a religious sense necessarily, but in a scientific sense. The fact that the laws of physics allow such richness is remarkable. Heat death does not remove this wonder. It amplifies it. It makes complexity feel less ordinary. Another insight is the acceptance of uncertainty. While heat death is the most likely outcome given current knowledge, the universe still holds unknowns. Dark energy is mysterious. Quantum gravity is unresolved. Initial conditions remain unexplained. The future may hold surprises, but uncertainty does not change the broader direction. Entropy increases, energy spreads, expansion continues. Heat death remains the dominant prediction. This teaches a balance between confidence and humility, confidence in physical law, humility about incomplete knowledge. Another realization is the idea that the universe is not optimized for comfort. It is optimized for stability. The laws of physics do not prioritize life or intelligence. They prioritize energy conservation and entropy increase. Life exists as a byproduct, not a goal. This reframes humanity's place in the cosmos. We are not the purpose of the universe. We are participants in its evolution. Another important reflection is the role of scale. Human lives are short, civilizations are brief, galactic eras are long. Cosmic timelines dwarf everything. Heat death reminds us that our scale is tiny. But tiny does not mean insignificant. A short poem can be meaningful. A brief moment can be profound. Scale does not determine value. Another insight concerns the narrative of existence. Heat death completes a cosmic story, beginning with extreme simplicity, rising to complexity, returning to simplicity. This arc is elegant. It is not chaotic. It is structured. It is governed by physical law. The universe is not random chaos. It follows patterns. It evolves. It stabilizes. Heat death is the final stabilization. Another reflection is the idea of cosmic responsibility. While humanity cannot stop heat death, it can shape the quality of the present era. It can protect ecosystems. It can reduce suffering. It can expand knowledge. It can create beauty. These actions do not require eternal futures to be meaningful. They matter now. They matter within time. Another realization is the importance of curiosity. Curiosity is one of the most powerful responses to impermanence. Instead of despair, curiosity drives exploration. It motivates learning. It inspires discovery. Heat death does not discourage curiosity. It makes it more urgent. The universe offers a limited window to understand itself. Curiosity allows that opportunity to be used. Another insight is the emotional transformation that comes with cosmic perspective. When personal problems are placed against cosmic time, they often shrink. Not because they are unimportant, but because perspective expands. This can create resilience. It can reduce fear. It can encourage gratitude. Another reflection is the idea that heat death does not define the universe's worth. The universe is not valuable because it lasts forever. It is valuable because of what happens within it, because of stars and galaxies, because of life and consciousness, because of understanding and creativity, because of experience. Another realization is the importance of memory. While the universe will eventually forget itself physically, memory exists now. Human memory, cultural memory, scientific memory. These preserve fragments of cosmic history. They do not last forever, but they matter while they exist. Memory becomes a form of resistance against cosmic forgetting, not permanent resistance, but meaningful resistance. Another insight concerns the nature of endings. Endings do not erase beginnings. The fact that something ends does not invalidate its existence. A star's light does not become meaningless when it fades. A life does not become meaningless when it ends. A universe does not become meaningless when it reaches equilibrium. Endings give structure to stories. They give context. They give boundaries. Heat death is not the negation of cosmic history. It is its completion. Finally, the most profound realization is this: the universe is not waiting for heat death. It is living through its middle age. Stars still shine. Galaxies still collide. Life still evolves. Intelligence still observes. Understanding still grows. We exist during this extraordinary phase. We are part of the universe's brief moment of self-awareness. Heat death may be the final state, but it is not the present state, and the present state is rich, complex, dynamic, and alive. That is what makes existence remarkable. Not that it lasts forever, but that it happens at all. At the deepest level, heat death forces a final confrontation with how humans understand existence itself. When the universe is seen not as an eternal stage but as a temporary process, every familiar assumption begins to shift. Time becomes more than a clock. Space becomes more than a backdrop. Life becomes more than survival. Everything gains context inside a much larger cosmic rhythm. One of the most powerful lessons of heat death is the idea that permanence is not the natural state of reality. In everyday life, people instinctively search for stability. They build homes. They create institutions. They preserve traditions. They record history. All of this reflects a desire to make things last. But the universe tells a different story. At the largest scale, nothing lasts forever. Stars burn out. Galaxies fade, atoms may decay. Space itself stretches beyond usefulness. This does not make stability meaningless. It shows that stability is local and temporary. It exists within limited windows. Heat death teaches that permanence is not a property of reality. It is a temporary illusion created by slow change. Another important realization is that the universe does not measure success the way humans do. Human success is often defined by growth, accumulation, and expansion. More territory, more energy, more influence, more control. Cosmic evolution does not reward endless expansion. It does the opposite. It disperses energy, it spreads matter. It dissolves concentration. The universe naturally moves away from accumulation and toward uniformity. This suggests that endless growth is not sustainable even on the largest scale. It reinforces the idea that balance, efficiency, and adaptability matter more than domination or infinite expansion. Another deep implication is the relationship between heat death and freedom. At first glance, a universe with an inevitable ending may seem restrictive, but in another sense, it removes unrealistic expectations. There is no requirement to achieve eternal perfection, no obligation to build something that lasts forever. The universe does not demand immortality. This can be freeing. It allows existence to be about participation rather than preservation, about experience rather than permanence, about engagement rather than endless accumulation. Another important shift involves the meaning of time. Humans often see time as an enemy, something that steals youth, erodes memory, and brings decay. Heat death reframes time as the very thing that makes complexity possible. Without time, stars would not form. Without time, life would not evolve. Without time, consciousness would not emerge. Time is not just decay, it is creation. It is transformation. It is opportunity. Heat death does not eliminate the importance of time. It highlights that time is a limited resource for complexity. That limitation gives time value. Another powerful lesson is the importance of rarity. The universe contains vast emptiness and silence for most of its existence. The era of stars, planets, and life is rare. Conscious observation is rarer still. This rarity gives weight to existence. It suggests that complexity is not guaranteed. It is fragile. It depends on precise conditions. That fragility makes it precious. Another perspective involves the relationship between chaos and order. The universe begins in extreme order, low entropy, simple structure. Over time, it becomes more complex, then eventually more uniform again. This arc shows that order and chaos are not opposites in the way humans often imagine. They are stages in a process. Order allows complexity to form. Complexity accelerates entropy. Entropy leads to equilibrium. This cycle reveals that creation and dissolution are not separate events. They are connected phases of the same cosmic journey. Another important realization concerns the illusion of centrality. Humans naturally place themselves at the center of experience. It is unavoidable from a subjective perspective, but heat death forces a recognition that humanity is not central to cosmic destiny. The universe does not evolve for human comfort. It does not preserve complexity for human benefit. It does not protect intelligence from thermodynamics. This can feel humbling, but it can also be empowering. It removes the burden of cosmic responsibility. Humanity is not required to save the universe. It is free to focus on improving life within its own scale. Another insight involves the difference between cosmic fate and personal meaning. Heat death describes what happens to the universe as a whole. It does not dictate how individuals experience life. Personal meaning exists at human scales. It emerges from relationships, creativity, curiosity, and understanding. Cosmic endings do not erase personal experiences. A sunset is meaningful even if the universe ends trillions of years later. A discovery matters even if knowledge is not eternal. A life has value even if species are temporary. Heat death does not cancel meaning. It contextualizes it. Another deep implication is the role of uncertainty. Even though heat death is the most likely outcome, physics is not complete. Unknown phenomena may still exist. New discoveries may reshape understanding. This uncertainty does not invalidate current predictions. It simply reminds us that knowledge evolves. This balance between prediction and mystery is part of science itself. The universe is not fully known. Heat death is not the final word. It is the best model given current understanding. Another realization is the importance of adaptability. Life and intelligence survive by adapting to changing conditions. The universe itself is constantly changing. Heat death represents the ultimate environmental shift. While humanity will not survive that far future, the principle remains relevant today. Adaptability, not rigidity, allows survival and progress. This lesson applies to ecosystems, societies, and technologies. Heat death reinforces the importance of flexibility in a changing universe. Another reflection concerns the emotional relationship with cosmic endings. Some people respond with fear, others with curiosity, others with acceptance. There is no single correct emotional response, but all reactions share one feature: they expand perspective. Thinking about heat death forces people to think beyond daily concerns. It encourages long-term thinking. It invites philosophical reflection. It pushes the mind beyond ordinary boundaries. This expansion of perspective is itself valuable. Another insight involves the idea of cosmic participation. Humans are not separate from the universe. They are made of the same matter, governed by the same laws, subject to the same entropy. When humans observe the universe is observing itself. When humans create art or knowledge, the universe is expressing its own complexity. Heat death does not end this participation now. It only sets a boundary far in the future. In the present, participation is still possible. Another important lesson is the relationship between scarcity and appreciation. Things that last forever are taken for granted. Things that are temporary feel more precious. Knowing that stars will eventually fade makes the night sky more meaningful. Knowing that life is rare makes biodiversity more valuable. Knowing that knowledge windows close makes discovery more urgent. Heat death transforms abundance into rarity at the largest scale. Another reflection concerns the role of responsibility. Humanity cannot stop cosmic entropy, but it can influence local outcomes. It can reduce suffering. It can protect ecosystems. It can expand understanding. It can build sustainable systems. Heat death does not remove responsibility. It clarifies its scope. Responsibility exists at human scales, not cosmic ones. Another insight involves the beauty of impermanence. Impermanence is often associated with loss, but it also creates variation, change, transformation, growth. Without impermanence, nothing would evolve, nothing would adapt, nothing would surprise. Heat death is the final stage of impermanence, but before that stage, impermanence allows everything meaningful to occur. Another realization is the connection between science and wonder. Understanding heat death does not remove mystery, it deepens it. It shows that the universe is not static. It has a narrative. It evolves. It transforms. Science does not replace wonder, it refines it. Another reflection involves the idea of cosmic maturity. The universe today is in a middle age. It is no longer the chaotic early universe. It is not yet the quiet heat-dead future. It is mature enough to support structure, but not yet exhausted. This middle age is where complexity peaks. It is the era where life and intelligence appear. This makes the present moment cosmically significant. Finally, heat death teaches one simple truth. Existence is not defined by how long it lasts. It is defined by what happens within it. Stars shine. Galaxies form. Life evolves. Intelligence understands. These events do not need eternity to matter. They matter because they occur. The universe may end in silence, but before that silence, it speaks through light, motion, complexity, and consciousness. And for now, it is still speaking. As the full picture of heat death comes together, one final truth stands above all others. The universe is not rushing towards its ending. It is unfolding through it. Heat death is not a sudden collapse. It is the quiet completion of a long transformation that began with the birth of space and time. And within that transformation, everything meaningful that has ever existed finds its place. From the first moments after the Big Bang, the universe was set on a thermodynamic path. Extreme order created the conditions for complexity. Expansion created space for structure. Gravity created stars. Nuclear fusion created elements. Chemistry created molecules. Biology created life. Intelligence created understanding. Each layer emerged from the previous one, forming a chain of increasing complexity. Heat death does not erase this chain, it completes it. The final state of equilibrium is not a rejection of creation, it is the end result of the same physical processes that allowed creation to occur in the first place. The laws that govern energy flow do not change direction, they simply run their course. This realization transforms the meaning of an ending. An ending is not necessarily destruction, it is closure, it is resolution. It is the point where a process reaches its natural limit. In this sense, heat death is not tragic in the way humans often imagine. It is neutral. It is not cruel. It is not intentional. It is simply the universe reaching the most stable configuration available to it. Another profound insight is that the universe does not measure value by duration. Stars burn for billions of years and then fade. Civilizations rise and fall. Species appear and disappear. Even galaxies will eventually dissolve. Yet none of these processes are meaningless. They are meaningful because they exist within time. Value is not derived from eternity. It is derived from participation in existence. The universe does not require permanence to create significance. It requires conditions that allow interaction, experience, and complexity. Another powerful realization is that heat death highlights the uniqueness of the present moment. Right now, the universe is alive with structure. Energy flows. Stars shine. Life evolves. Knowledge grows. This phase is not guaranteed. It is temporary, and that makes it rare. Cosmic rarity is not about scarcity of matter, it is about scarcity of complexity. The era in which the universe can support conscious observation is extremely short compared to the full timeline of cosmic history. We exist inside that narrow window. This makes our moment cosmically special, not because it is privileged, but because it is statistically rare. Another insight concerns the role of humanity within this window. Humans are not passive observers. They are active participants. They transform energy. They create information. They build structures. They expand understanding. While humanity cannot alter the ultimate fate of the universe, it can influence what happens within the current era. It can shape culture. It can protect ecosystems. It can expand scientific knowledge. It can reduce suffering. These actions matter now. They do not require eternal cosmic impact to be meaningful. Another realization is the importance of perspective. Heat death expands the scale of thought. It forces consideration of billions and trillions of years. It places human history into context. This perspective does not diminish human experience. It enriches it. It shows that our existence is part of a much larger story, a story that includes cosmic beginnings, stellar evolution, biological emergence, and eventual equilibrium. Another important lesson is the difference between inevitability and hopelessness. Heat death is inevitable according to current physics, but inevitability does not imply despair. It simply describes direction. Knowing that the universe will eventually reach equilibrium does not remove the possibility of joy, discovery, creativity, or meaning in the present. It encourages focus on what can be influenced, not what cannot. Another insight is the role of acceptance. Acceptance is not resignation. It is understanding reality as it is. Heat death invites acceptance of impermanence, not as loss, but as a natural feature of existence. This acceptance can reduce fear. It can reduce anxiety about permanence. It can shift attention toward experience and presence. Another powerful realization is the idea that the universe is not separate from observers. Observers are made of the universe. When humans think about heat death, the universe is reflecting on itself. This self-reflection is rare. It exists only during the complexity window. It represents a moment when the universe becomes aware of its own trajectory. This is one of the most extraordinary features of cosmic evolution. The universe produces minds capable of understanding cosmic fate. Another insight concerns the relationship between science and wonder. Understanding heat death does not remove mystery. It deepens it. The fact that physical laws can produce such a vast evolving cosmos is astonishing. The fact that simple equations can lead to galaxies, life, and consciousness is remarkable. Heat death does not make the universe boring. It makes it more impressive. It shows that the universe has a coherent narrative. Another realization is that the future of the universe does not define the worth of the present. The universe's ending does not retroactively invalidate its history. Stars that burned still burned. Life that lived still lived. Discoveries that were made still changed understanding. Heat death does not erase past reality. It only prevents new complexity from arising in the distant future. Another insight is the importance of curiosity as a response to impermanence. Instead of fearing the universe's end, curiosity encourages exploration of its structure, origins, and laws. Curiosity transforms inevitability into motivation. It turns limited time into opportunity. It drives humanity to understand as much as possible while observation is still possible. Another realization involves the concept of cosmic gratitude. Not gratitude in a religious sense necessarily, but appreciation of existence. The universe did not have to allow complexity. It did not have to produce stars. It did not have to produce life. Yet it does. For a limited time, this creates an opportunity for appreciation of the present. Another important lesson is the idea of responsibility within scale. Humanity cannot control cosmic fate, but it can control human behavior. It can choose cooperation over conflict. It can choose sustainability over exploitation. It can choose knowledge over ignorance. Heat death does not absolve responsibility. It clarifies its boundaries. Another realization concerns the role of storytelling. Heat death completes the cosmic story: beginning, evolution, complexity, equilibrium. This narrative structure helps humanity understand its place in the universe. It transforms cosmology into a meaningful framework, not just numbers and equations, but a story of transformation. Another insight is the emotional maturity that comes from confronting cosmic endings. It encourages acceptance of mortality, not just personal mortality, cosmic mortality. This acceptance can lead to deeper appreciation of life. It can encourage compassion. It can inspire cooperation. Another realization is that the universe does not promise comfort. It promises consistency. The laws of physics operate reliably. They do not adjust to emotional preferences. This reliability is what makes science possible. It is also what makes heat death predictable. Understanding this can reduce the desire for cosmic favoritism. The universe is not unfair. It is indifferent, and within that indifference, complexity still arises. Another insight concerns the idea that the universe is generous with opportunity, but not with permanence. It allows stars to shine for billions of years. It allows life to evolve. It allows intelligence to arise. But it does not preserve these states forever. This balance between opportunity and impermanence defines cosmic history. Finally, the most important conclusion is this: heat death is not the story of nothingness. It is the story of completion. The universe does not collapse into chaos, it settles into stability. It does not end in fire or destruction, it ends in quiet. And before that quiet, everything meaningful happens. Stars light the darkness. Galaxies paint the cosmos. Life explores reality. Intelligence understands existence. Art expresses experience. Science uncovers truth. These are not erased by the future. They exist now. They matter now. The universe may eventually fall silent, but right now it is speaking, and we are here to listen.